Chapter 5 Torsion Part B Example 3 Parallel and Series in beams and shafts. In this example, we want to know if we have a three blocks with different materials with different cross-sectional area, what is the and fixed at both end, what is the delta at B, which is the point which the force P applies, and also reactions at A and D. To solve this problem, let's first solve it with a new method, then we will move and solve this problem in the parallel and series as well. Mm. So if we call this solution 1, in such problems, EA over L is important. This this approach called normalizing axial stiffness, and this is axial stiffness. And what that is, it says if we have the axial stiffness for the very first one, EA over the length, EA over L. For the second part, so if we call this piece 1, let's say 1, 2, 3. So let's take the EA over L, third one, the smallest one, as a base, and then we want to have the same, and the second one is 2 EA over L, and the third one is 3 EA over L. So by normalizing, we mean if we want to have a situation which take the very first one, I mean the smallest one, the third block, as a base, this is our base, and make the EA for the others as same as the base. So EA remains the same in all of them. So in that case, you can rearrange 2 EA over L by EA over L over 2. So this is this, they are identical to each other. Likewise, 3 EA over L is just EA over L over 3. So by this approach, we just normalize the numerator. Mhm. In in this case, one can say now we made all the material like in a similar format. So their EA is the same, the length changes. So the very first one remains with the base with the length of L. The other one uh, just goes by L length over 2, and the third one L over 3. So in that case, we can simulate our problem with a simple two fixed support beam, which a load P is applied at point B over here. Mhm. Let's see how we can uh, solve our problem. So to get the reactions at A and D first, and then get the displacement of point B. So it's like a vertical, we just convert the horizontal situation to a vertical part, and that's a fixed, two fixed end beam, simple beam, handling a concentrated load of P at a distance uh, from A to B. Let's have a closer look to the problem. So we want to know what RA is, what RD is, the length are provided, and a load P is applied, a concentrated load of P applied at the point B. So first, let's consider a situation in which a load P is applied at the center of the same beam. In that case, just due to symmetry, we do know each of the reactions are just a half of P. So that's a half of P. And RC, again, due to symmetry, is another half. So these two forces should cancel out the concentrated compressile force at the center, which applies top at the center. So let's consider a situation which we just move P to a location like here. So this is our force P, which applies at, let's say, a distance of what? A from support C and a distance B from the other support. In that scenario, weight is not distributed evenly. The force is not distributed evenly between the two supports. So the closer the support to the force handle the more weight. So one can easily say RC, it should be from the intuition, RC is bigger than RA. Now let's see how the equation goes. That says that's a P over L. No, let's put it this way. That's RA is P, L, RC is P over L. But this time RA goes by A, the other half. So force at reaction at A goes by a distance to the other section, and the R at C goes by the longer distance. So in that case, it's let's say P times B. Let's put it by a numeric value. So if this is 1/4 of L and B is 3/4 of L, so RA reaction at A is let's write it here. P over L times a is a quarter of L, 1/4 of L. And L cancels out. That's P over 4. It simply says our reaction at A handles a quarter of force, and likewise for reaction at C, it just P over L times 3/4 of L. L and L cancel each other, and it just goes by a 3/4 of force. So with the same logic, we can let's take a look to our problem. So if this is distance A and this is distance B, so in that case, let's see what is the total L. The length of total length is L over 3 plus L over 2 plus L. So that's 11 over 6L if you do the math. Then reaction at A is nothing but a let's P over total length LT times A. A is L over 2 plus L, so that's 3 over 2L, 1.5 L. And total length, we calculate that LT is 11 over 6L. So 3 over 2L at the numerator and over the denominator times the total force. That gives us the reaction of Ra goes by 9 over divided by 11 times P. So if that goes by that amount, the total is 11 over 11. This is 2 over 11 times force. So as soon as we do have the forces, what Ra is, what Rd is, we can we can just calculate the delta. So let's continue our problem. So as soon as we know what Ra and Rd is, one can easily calculate delta at any point in the structure. So that's 9, that's 2. Now let's delta B is NL over EA. If you start from here and just move to the right, you can see there is no other force on the first element but reaction at A. So that's our N times length of the element over EA, which is 3EA. Do the math, it gives you 3 over 11 times PL over EA. That's delta at a point B. You can calculate likewise delta at C. Mhm. That was a solution one, which is also a very simple solution to this problem. Now let's go a step further and solve the same problem with the beams in parallel and series. So if one can separate the structure from B at B, so forget about a this part. Just for now, forget about piece one, block one, which we already called that block one. Just consider a block two and three. Again, it's like a two spring which handles, this is spring two, this is three. Let's have it like here. This is second one, this is the third one. And they are just handling a force P. This is K2, this is K3. And that's the point of the force. It's a hint to a series condition. So that's K2 and K3 are in a series connection. Mhm. So K2 and K3, as you can observe in this figure, K2 and K3 handling a force P in at the center at one ends, and they are in a parallel situation. Sorry, in a series situation. So in series 1 over K equivalent is 1 over K2 plus 1 over K3. So if you remember, the very first one was EA over L, so it was 1 EA over L. The other one was 2 EA over L. And the last one is, or the very first one was 3 EA over L. So just for now, forget about EA, just go by the numeric value, then replace EA over L. So in that, in one can say K3 is 1, K2 is 2. So 1 over K2 is uh, 1 over 2. So in that, if you add them up, you will reach to K equivalent of 2/3 of EA over L. Mhm. And the combination of the 2 and 3 If you just consider this one as a K equivalent is in a parallel with K1. Mhm. So again, let's get rid of this part. So again, you can consider 2 and 3 like a equivalent spring. So in that case, due to loading, if it just take the one part by, for example, zero point 0.2 inch to the right, the other one should follow. So delta remains the same. So one can say K2, a KE equivalent of 2 and 3. So that's K is parallel to K1. And in parallel, KT is K1 plus K equivalent of 2 and 3. If you do the math, it gives you this is 1 is a, a 3 EA over L. So just we have EA over L here. So a 3, which is the stiffness of K1, plus 2/3, which is our K equivalent, 2 over third. If you add them up together, you will get the K total stiffness of 11 over 3 EA over L. Mhm. And then delta B in a parallel case, which K1 is in parallel with K equivalent of the other half, is nothing but the force over total K. You remember in parallel connection, delta remains the same in both. So P over total stiffness of 11 over 3 EAL gives you delta B is again the same numeric value which we calculate in previous solution. And the first solution was normalizing solution, and the other one is a beams or pieces in series and parallel. Thank you.